Remember photo at 3:30
Swee
after
Hong
talks
Chan.
today?
Swee Hong Chan?
Um,
Exactly.
and banquet
you
is
so
also
much.
today at 6. In the main building, where we have the cafeteria, just outside the cafeteria, there's a large area with seating, and it will be there. Yeah, and you can just show your badge to get into the building for the banquet.
Good. Okay, so welcome to the morning session. The first talk will be by Swee Hong Chan on complexity of log-concave inequalities for matroids.
Thank you very much for the clap. So first, I would like also to thank all the organizers for arranging this great workshop, and most importantly, I also want to thank everybody here for coming today at this morning. Okay, so the main character of today's talk is the log-concave inequality, and here is what I mean by that. So for today, we will always have a sequence of a1, a2 up to an. These will always be a non-negative integers. And we say that this sequence is log-concave if, for any case strictly between 1 and n, the square of the kth number will always be greater than the product of k plus 1 number and k minus 1 number. For example, this sequence here, sorry, is a bit low, is log-concave sequence. It's because 9 squared is 81. 81 is greater than, as far as I know, 4 times 16, which is 60. Okay? So this is log-concave. And the quintessential example, probably the first example of a sequence that we know that is a log-concave, is the binomial coefficients. Here n is fixed, and k ranges from 0 up to n. And this sequence, we know it's log-concave because, well, we can simply do direct computation. We take this ratio, we did the calculation at the train, is equal to 1 plus 1 over k times 1 plus 1 over n minus k. K is between 0 to n, therefore this number is always greater than 1. That's how we know this is log-concave. Okay, everything good so far? Feel free to interrupt me at any time, or if I speak too fast. Okay, the second example comes from the permutation theory. Here, AK will be the number of permutation of n elements with exactly k inversions, where an inversion of a permutation is a pair of I and j, so that I is less than j, but pi I is greater than pi j. So you inverse the order. That's why you call it an inversion. Okay? And already for this sequence, you cannot prove that this is log-concave by direct computation. This is because, to the best of my ability, there is no known explicit formula for this constant AK. Instead, what people usually do is that they write a generating function for this sequence, and then they see that, what a coincidence. This is what we call the Q analog of n factorial. More importantly, it is a product of these polynomials. All the coefficients are 1. In particular, it is a log-concave sequence. It's a well-known result that says that the product of polynomials preserve the log-concavity of the coefficients. And that is how we conclude that the original sequence is log-concave. Okay? Okay, and this one is the final example for today for our log-concave sequence. This is called the Mason's conjecture for matroid, or sometimes people call it the first Mason conjecture, because Mason made 3 conjectures. Okay? So here, let M be a matroid. Let AK be the number of independent set with exactly k elements. So for example, if this is a graphical matroid, this is the number of forests with exactly k edges. Okay. The log concavity of this sequence was first conjectured by Mason in 1972, and as far as in comparison to the other 2 problems, this one is actually a very difficult one. This is because, as we see here, it was first conjectured like around 50 years ago, and it was only solved recently after the work of many emerging mathematicians. And the complete solution was obtained by Karim Adiprasito, Juniher, and Eric Katz in 2018 by using this new theory that is we now call it the combinatorial Hodge theory. This result and this theory was cited by the International Mathematical Union as one of the reasons, among many reasons, but still one of the reasons, of them awarding Junhe with the Fields Medal in year 2022. Okay? So these are the 3 examples of log-concave inequalities. Any questions so far? Everything good? Okay. Okay. So now we have seen 3 log-concave inequality. First 2 is at the level of homework exercise. The third one took almost 50 years and the work of many brilliant mathematicians, one of them a Fields medalist, to completely solve the problem. So intuitively, it's very, very, very clear. The third inequality is more difficult than the other 2 inequalities, right? But for now, let me just play a devil advocate. Let me say something like this, something very controversial. Hey, Swee Hong, maybe there is a trivial proof for Mason's conjecture. It's just that nobody has worked hard enough to find it yet. You know, after all, maybe everything in combinatorics is trivial, right? Okay. Okay. By the way, I completely disagree with the devil's advocate. What he said is completely outrageously wrong. But we are all here mathematicians, right? So if I want to show that my devil's advocate is wrong, I should not just go and scream at him that you are wrong. What I should do is that I should give a rigorous proof. I should give a rigorous justification why Mason's conjecture should be more difficult than all the other inequalities that we solve today, and maybe even most other inequalities in combinatorics. That is our goal today. We want to show that the devil's advocate is wrong, that Mason's conjecture is really something that you cannot prove by most combinatorial means or most elementary means. Okay. Any questions so far about our goal? Okay. No? Okay. And first of all, now I would like actually to apologize that unfortunately I still do not know how to do this goal for exactly the Mason's inequality. That's why, in order to settle for the next best thing, today we will instead show that a slight generalization, so something that's a bit stronger than Mason's inequality, cannot be proved by any elementary mean, cannot have any injective proof. That is what we are going to show today. Okay? And this slightly more general Mason's inequality is now known in the literature as the Stanleyian inequality. Here is the statement. Let M be any matroid, can be regular, can be binary, can be anything. Fix a subset S of the ground set. Let Bk be the number of bases of the matroid such that the number of elements coming from this fixed subset S is exactly equal to K. The statement of the theorem is that this sequence B1, B2, B3 is an ultra log-concave sequence. The ultra comes from the fact that you actually normalize by the binomial coefficients. Okay? And this theorem was proved in the 2 different phases by 2 different people. The first phase was done by Richard Stanley in 1981, where he proved this inequality for all regular matroids. And Stanley's proof was very beautiful. It was very elegant. What he did is that he interpreted all these numbers Bk's as the mixed volume of this polytope that's called the Zunotopes. And then, by using the Alexander-Fenchel inequality, which is like a log-concave inequality for mixed volume, this inequality just follows immediately. Okay? The second phase was actually just completed last year by Alan Yen, who back then was a student of Junhe in Harvard, where he used the technique of Lorentzian polynomials to finally solve the problem, not only for regular matroids, but for all matroids. Okay? And I claim that this Stanleyian inequality is a generalization of Mason's inequality in the following sense. Consider the original matroid M in the Mason's inequality. We construct a new matroid M prime, which is the direct sum of M with the free matroid. And we choose our set S in our Stanleyian inequality to be the ground set of the original matroid M. It then follows, almost by definition, that Ik, the number of independent sets with exactly K elements for the old matroid, is actually equal to the number Bk for the new matroid M prime, normalized by 1 over I factorial, just by a constant. Okay? In particular, Stanleyian inequality told us that the right-hand side is log-concave, and therefore the left-hand side, which is the Mason's conjecture, is also log-concave. Okay? So this is like a one-page proof of Mason's conjecture, okay? By using something stronger. Okay. And in fact, actually, Stanley Yan, they prove a more general inequality that we now sometimes call it the full version. This is saying that you can actually also include extra D subsets, S1 up to SD, you fix them. And you can additionally ask for extra assumptions, which is asking that on top of having intersection with the set S equal to K, the basis intersect with S1, S2, SD will be equal to the fixed number L1, L2 up to LD. And the one that we saw before is a special case when K is equal to 0. And the claim, which is also proved by the same by Stanley and Yan, is that this sequence is still a log-concave sequence. In fact, as far as I know, the proof of Alan Yan is such that you need to actually prove it for general case first and then specialize for K to equal 0. It's a bit hard to try to prove it directly. Okay. Sorry, D equal to 0. Yes, thank you so much for correcting my mistake. Okay. So this is the inequality that we will discuss, we will focus on today. Before I proceed further, are there any questions? Let me get some water. Yes, yes, you can think of this as the intersection theory of the Hotz-Riemann. And what Alan Yan did, this is a Lagrangian polynomial. So this is like you can think of, so this is like the multivariate version. And then you for the case K equal to 0, D equal to 0, you specialize everything to be, all the other coefficients to be equal to 1. Yes. Yes. Any other, thanks for the question. Any other questions? Yes, please. I guess, so the question is that what is the limiting object for this? If you take, like, let's say a large matroid or let's say a random matroid. That is a very good question. I don't know. It has not. This is a. I will guess probably it will probably convert to something canonical. Whether or not it's normal distribution is probably an open question that is still unknown. Okay. No. Okay. Now there's no. Let me continue. Okay. So let me now come back to being the diverse advocate. Okay. So I look at these inequalities, and I see that, hey, Swee Hong, both the left-hand side and right-hand side, they both have combinatorial interpretation. They both is the number of bases of some matroids. So, an elementary proof of this inequality will be to show that, you see, we define a simple injection that sends elements from the right to everything on the left. That would be a simple proof of Mason's inequality. Simple proof of Stanley inequality. In particular, it will be a simple proof of Mason's inequality, right? And of course, we need to define rigorously what does the word simple here in the simple injection. And fortunately, there is already more or less a commonly accepted way to do it in combinatorics. And that is called the combinatorial injection. So an injection F sending maps elements from A to B, we say that this thing is an combinatorial if for any element X in A, the image F in B can be computed in polynomial time with respect to the length of the input X. Okay? So it's efficient to compute. And because it's injection, we need to define the pre-image. We need to define the inverse map. So given element Y, in the codomain, first is that you need to figure out if this element is inside the pre-image. And of course, you should always be able to do this in polynomial time. That's part of the assumption. And if it is actually part of the pre-image, so part of this red picture, then computing the pre-image in the blue picture in A should also take polynomial time. This is the definition of combinatorial injection. And here's an example of such injection. This is the binomial inequality that we saw at the beginning. And this inequality actually has the following lattice path interpretation. Let KACBD, where A, B, C, D are 4 points in the integer lattice, let this be the number of pairs of non-northeast lattice paths. So this means that the paths either go up or go right, from A to C and B to D. So like in this picture. I claim that with this choice of A, B, C, D, so these 4 points in the integer lattice, KACBD will be equal to the left-hand side of binomial inequality. KADBC will be the right-hand side of the binomial inequality. Okay? And therefore, if I want to show an injective proof of this binomial inequality, I can do so by defining an injection sending path from the left to path from the right. And we defined it in the following way. Because of the position of A, B, C, D, these two paths must always intersect at some point, right? And then you just find the first intersection. This takes linear amount of time with respect to the length of the path. Then, from the first intersection, you swap the color of the path after that. Red becomes blue, blue becomes red. This defined injection is simple to verify that in this defined injection. And you see that all of the, how it's defined, that to compute a new path from the old path, it takes linear time. In particular, it takes polynomial time. And therefore, this injection is combinatorial. And as far as I know, virtually all combinatorial, all injective proof in the literature, they all belong to this form. Okay? Most of them, with some few exceptions. Okay, and our result, our claim is that there is not only that there is no combinatorial proof known, in fact, there cannot possibly exist one. You cannot ever find a combinatorial injective proof for Stanleyan inequality under the assumption that MP to the power of MP is not equal to co-MP to the power of MP. So I would like to apologize that because of time restriction, I will not fully define what this means. But for the purposes of this talk, it is probably a good idea to think of this as a slight generalization of P not equal to MP. So this means that if you show this is true, you will still get $1 million. But rather than getting it from a Turing Millennium Prize, you get it from the Turing Prize. Okay. Okay. So this is our first main result, and if there are no questions, I will continue to actually a generalization of this result for something that we know as a sharp P in the complexity literature. Okay. Everything good? Okay. And to define I will define sharp P in the next slide formally, but just to build intuition, here is an informal definition. So I like to think of sharp P, this as the class of problems of counting the number of objects that satisfy some property. And this property must be simple to verify, that this property in a way must be more or less combinatorial. For example, here is a problem in sharp P where we are counting the number of proper tree colorings of a given graph. The object here we are counting is a number of colorings, and the property, the simple property here is checking if the coloring is proper or not. Okay? So this is the informal definition. Here is the formal definition. And to do that, I first need to define what is MP. So MP, this is the class, there are many definitions. The one that's most relevant to us is the following form. That you define MP as a problem for asking for the existence of a solution to a given input. And the validity of the solution must be verifiable in polynomial time. For example, this is a problem in MP, which is that given a graph G, we ask if the graph has a proper tree coloring. So here, the solution will be a proper tree coloring, and checking that if a coloring is proper or not, you can simply check for every edges, right? There are at most n square edges. In particular, it's quadratic time. In particular, it's polynomial time. And sharp P, this is the we are asking similar thing, except that if instead of asking for existence of a solution, we are asking for the exact number of solutions. So in this case, a problem in sharp P will be to count the number of proper tree colorings of the graph, of a given graph. Okay? And under this notation, under this definition, we can now state our real main result. So consider this number in the Stanleyian inequality, right? By Stanleyian inequality, this number is a non-negative integer. In particular, you can define a counting problem to ask for the exact value of this thing. I claim this counting problem cannot possibly in sharp P, assuming something that will win us $1 million, assuming something that is a bit stronger than P, not equal to MP. Okay? Now, notice that the left-hand side and right-hand side of this inequality, they are both have covenant interpretation. They are both counting number of bases of something. In particular, they are in sharp P. So this means that this number is actually not very big. And there are indeed many inequalities in combinatorics that do not belong to sharp P, but they are not there usually for trivial reasons, like maybe all the numbers involved are too big, like exponential to the power exponential to the power exponential. Then yes, we cannot do anything. But in this case, the two numbers here are actually already not very big because they're in sharp P, but the difference, which is smaller, which suppose intuitively should be simpler to compute, somehow actually become harder to compute. Okay? And in the last 2 minutes, let me just come back to our goal. Remember that our goal is to show that Stanleyian inequality is strictly more difficult than the binomial and permutation inequality. And let's just see if that's the case. Let us use our result to see that. And to do that, I need to figure out the complexity of the other two inequalities. For the binomial inequality, remember that we have this lattice path interpretation as this difference, which is the number of lattice paths that is not intersecting. In particular, it's easy to see that this is a covenant interpretation, and it can be shown that this is actually saying that this thing belongs to sharp P. Okay? Second one, the permutation inversion. This one, there's also an injective proof by Miklos-Bona in 2012, but there's actually an easier way to see why this belongs to sharp P. The way to see that is that these coefficients, they have this nice generating function. In particular, this thing, you can use this formula to compute every single one of these coefficients in polynomial time. And so you can also compute this difference also in polynomial time. And there's a theorem in the complexity theory that anything that is computable in polynomial time also belongs to sharp P. Okay? So, putting everything back together, in conclusion, today we see 3 log-concave inequalities, right? We have shown that the first two belong to sharp P. The third one, which we only recently can prove by using all these advances in Matroid theory, does not actually belong to sharp P. That it is actually more difficult than, it actually cannot be proved by almost all combinatorial means. This differentiates the third inequality from the other two inequalities, which is exactly what we promised. That now I hope that my DVOX advocate will admit that he is wrong. Okay? That's all I want to say. Thank you very much for listening.
Fantastic. Thank you very much. We're a little short of time, so unless anybody has just one very quick question. Yeah, okay.
Yes.
Oh.
What do you know in complexity about the Stanleyian defect? Like, do you know that it's hard or complete for some complexity class?
Let me just go
You
back.
know it's not in number P, but
This one?
the defect.
Yes.
So you're saying the defect, the Stanleyian defect, is not in number P, in sharp P.
Yes.
So do you know that, like, is there some higher class that you do know that it's in, and is it complete or hard for some higher class?
There's okay. The question is that where is exactly this thing belong? Yes. So one thing we know is that this class belongs to this thing that's called gap P, which is the difference of two numbers in sharp P. And if the next question is that I think you're asking if do we know this number is sharp P hard or gap P hard? In that case, there's still actually open problem. Yes. So in a way, this actually the beauty of this technique is that we can actually prove something not in sharp P without showing it's sharp P hard, because there are some conjecture on some numbers in algebraic combinatorics that we know is not sharp P hard, but we still believe it's not in sharp P. Yes. Thanks for the question. Yes.
Great, thanks a lot. Let's thank Swee Hong again.
Thank you very much.